You may have different answers, that's all welcome.
It's basically the properties that define the device or the material we are.
Okay, so it is basically the, I think you try to mean that probing the properties, right? Probing the properties. The characteristics means the properties here. Okay. Any other perspective we have?
The response of the certain device to a specific input.
Good. So how does it respond to a certain stimuli?
Yes.
Right. So thank you. So input versus output thing.
Yes.
Right. So that's very good. Another perspective. Any other perspectives? Okay. Let's say to find another perspective. Let me now draw your attention to another question. Why do you think we need this? One question. You said you were to find the properties, understand the properties. It's kind of understand. You said it is a response or study the response, right? To how does it respond to a certain input or stimuli? Why? Why do you want to do that? Why do you want to know the properties? Why do you want to understand the response to a stimuli?
We will be able to use it in certain applications.
Okay, so the knowledge of the properties gives us the ability to understand how to use it, let's say, application wise. Okay, why do you understand? Why do you want to understand the response to a stimuli?
We need a mathematical model.
So we want to build a mathematical model. Okay, why do you want to build a mathematical model?
Then only we will be able to solve the differential equations providing the circuits where it will be applied.
So probably what I'm trying to say is that we want to build a model so that actually from what I think is that we build a model so that we can study a large number of them without going into detail of each of them. Right? We just get some essential parameters, we fit in the model, and that kind of describes the entire system for us. Isn't it? I think that's why we build the model. But what I am trying to draw your attention to here is one essential reason that you are missing here, or let's say one essential point that you are missing here, is the fact of reliability, reproducibility, and quality, right? These are the things that are also important. So, to know the property, yes. To understand the response, build the model, yes. These are all important while we're characterizing. But another important point we often forget is that we also need to understand or measure the quality of the product of the device, right? So, in industry, we'll have something called quality check, quality inspection, QI, QC, like that, right? Where a batch is made, the millions of transistors are made, maybe 10 transistors are taken from that each batch, and then they are screened on a daily basis and studied, right? The purpose is so that we know if there are some defects, okay? And if there are some defects, sometimes the entire batch is stopped, right? And then more inspection is done on them. So finding the quality, finding presence of any defects or quality, these are also another reliability. These are also another aspects for which characterization is needed. So characterization can have multiple motives, and some of them you already mentioned. Some of them probably are still missing here. But for whatever reason, we need to do different kinds of measurement. And something we also discussed during the last talk was we touched upon some of the measurement. Because for example, someone asked me, how do we measure so and so things? And I think I explained or tried to give a few things, something optical, something magnetic, right? Something electrical. Probably we touched upon some of those things. Huh? So in the device world, the characterization begins. Okay, the characterization begins right from the substrate itself. So if I talk about a transistor also, the first part of the process is to develop the substrate. Agreed? So the substrate comes first. Be it a silicon substrate, with a silicon oxide substrate, or whatever substrate we are choosing. That substrate is the first thing. Okay? So the first part of the job we have to find out the defects in that substrate itself. If it is a silicon crystal, for example, okay, how will you find out if the crystal is good, bad? How will you characterize it? What are the essential properties? Let's say you will check in a silicon wafer, the substrate. Let's say if I frame the question in a different manner, if we talk about a wafer, okay, some of you may have heard about a wafer, some of you may not have heard about a wafer. That's okay. For those who have not heard, I'll define that. If you see, if you have some, maybe you have seen some pictures, I don't have the picture or else I would have shown you. It's like, huge disc kind of things, and they are like sometimes multicolor you can see, or sometimes just grayish, bluish, depending on the lighting condition. Okay, so this is like a silicon, thin silicon, let's say like a papad or whatever you call it. Like if I want to use that analogy to describe it, like a disc of silicon or silicon oxide generally. Okay, so this is a wafer. Okay, it's 6 inch, 8 inch sometimes. Okay. So this is the beginning of the process of making a device. If I talk about the general solid state devices, for example, okay, that's the first thing. So once that silicon wafer is made, how do you characterize? So what are the essential properties? If I want to buy a silicon wafer, how would I buy it? How do I tell the vendor, for example, that this is the silicon wafer I want? What are the properties I'll quote here?
There must have been some electrical properties.
Sure. Structural property.
Temperature.
Temperature probably will be more dependent on the ambient, but maybe temperature tolerance maybe we can talk about. Doping. What else? Optical properties. If I'm talking about an optoelectronic device, maybe yes. Oxidation, yes. If it is oxide, for example, if I say it's a silicon oxide, for example, then oxidation state. Okay. Anything else? Let's say we have enough properties now. Maybe there are some we are missing, but let me highlight what we have just mentioned so far. Electrical property. How do you like to measure it? What parameter would you choose? Conductivity or resistivity, as the inverse of it, right? Very basic. Doping, someone said, right? So if it is doping, then what would I want to do? What would I like to specify? So either I would specify the doping type, one thing, N or P, correct? The second thing would be to doping concentration. That means carrier concentration. Is it heavily doped? Is it lightly doped? Is it medium doped? Because the doping concentration can be a huge range, isn't it? And depending on that, your Fermi level will be shifting, right? So, depending on the device you want to make, for example, you want to make a high mobility gallium nitride device, for example, right? Which are called high electron mobility transistors, HEMT, right? For that, you will need a very highly doped, most likely N-type semiconductor, right? So then you will look for a special doping. You will look for high doped. Okay, you will say that okay, N-type, this kind of concentration I need of doping, right? So this is one parameter, right? You are defining the parameter. Someone says structural, right? So structural, how do you define the structural?
10010.
Correct. So the crystalline structure, is it 110, 100? What kind of crystal structure it is, right? So these are the things I have specified. Now when it comes to me, the vendor has provided me or provided you, you have bought it, right? He has provided you. Now you need to verify it. You don't know the vendor. First time he is giving you don't even know he is giving you some kind of CT disc and telling you this is a silicon wafer. I'm just kidding, but who knows, right? So we need to characterize it, right? We need to measure something. So what will you measure? You will measure the same parameters. How will you measure the resistance, resistivity? Apply voltage and measure the current, right? Something like that. Okay. What else? What was the second thing? Doping. How will you measure?
Mobility.
Okay, but how?
Maybe Hall.
Huh?
Hall.
Hall. Yes, exactly. So very widely used measurement. Hall. Are you familiar with the Hall measurement? Anyway, we have one slide on that, so we'll come to that. What was the third thing? Structural. How do you measure? 100, 110, XRD, exactly. So see, you all do it, you all know it, right? And some of you probably know better than me, right? I am only here as the source to ignite you to encourage you to just share with your colleagues here. That's it. Okay. So yeah. So this is the necessity of characterization. This is the necessity of measurement, and this is the first step. Okay. Some more things I didn't ask or we didn't mention here are, for example, is the silicon wafer having defects? Because, for example, if I perform XRD, it will only give me a broad peak. It will only tell me broadly that this is 110 or 100. However, there can be defects, right? There can be stress induced in the wafer because of some manufacturing issue, right? And if I build on that stress, then my device will also have that stress translated because of something called the epitaxy, right? For people who already know epitaxy, they will understand what I am saying. But people who don't understand it is like, for example, if your foundation is somewhat like in a building, if the foundation is like a bit tilted or skewed some way, and you start putting bricks on them, then the brick columns will also be tilted, isn't it? That is epitaxy. Okay. So these are the things also need to be tested. And for that other mechanisms, for example, can be used. We will now have a look at some of the mechanisms that are used. Because it is organized by the electronics department, and I assume that some of the resistivity and all you are probably more familiar with. So, and since I have limited time also, I will try to go first with more of the material characterizations, okay, which basically are more of imaging, measuring the composition, measuring the structure, measuring probably the bonding states, right? These are the things I will first cover, and then we will go to the electrical one. Okay. So let us begin. Maybe just unplug it and plug it again. Well, battery is there because the laser is still on. Probably the whole world wants us to stop today. Enough of FDP for the entire week. These are all messages. But we as human beings are defying. We will defy it, and we will still continue for at least 1 hour before we surrender. You can give me the pointer. The pointer is there. This slide is not necessary. Please move. Next. Okay, so I think we here. So if you look at these images here, no. So these are devices. Okay, so you have the gate, you have the drain, you have the source, and all those things, right? And then you have the P dot region, the dot regions here, and the well here. So all of these are imaged using probably ACM or TM. But what the message I wanted to give you here is that this kind of imaging is very necessary. I mean, we did not talk about imaging here, but this kind of imaging is also necessary. Sometimes, for example, you might find that your gate is overlapping with your source or drain, right? So how do you know that? The only way to know that is, by looking at the device response, probably you will have an idea. But if you just study the device response, it is not conclusive. You will really not know if the anomaly that you see in your device response is actually because of a gate tray overlap or something like that, or something else. So to conclusively find out, a direct probe is needed, and that kind of imaging, for example, can be used. So let's keep on the slides. No need. Okay, so let us talk about some kind of probe sources, okay? And and there can be so many kind of probe sources, and I think many of you are familiar with many of the sources. So let's start naming some of the sources. Let's begin with the probes you have already used. If someone has used something, so have you used XRD? You have used. So you have used an X-ray source, right? Any other any other person here who has used any source like that, X-ray or any other source you have used for any kind of probing? ACM you have used. So then what was the source there? It's an electron. Okay. Anyone else? So TM also you have used, and then again electron you have used as a source. Anyone else? Sorry? FTIR. So what is the source there? Infrared, but it's in the it's a photon. Right? What else? Huh? UV, again is like the electromagnetic spectrum, right? What else? AFM you have used. Now that is a whole different game. That doesn't use any energy source, electron, photon, so on, right? It is a completely different one, which is in the broader scheme of things called a surface probe microscope, right? Fine. So that's another probing. We will come to that. In this one, then we have so far then talked about. We have talked about electron source in SEM, in TEM. What is the distinction? TEM it is transmitter. So in scanning it is kind of diffraction rather, and in case of TEM also it is partly diffracted and partly transmitted. Okay. Now the energy source in a SEM and in a TEM. What is the difference? First thing is, what is the energy source? Electron source. How do we generate that electron? Electron gun. And electron gun, there are two basic ways how the electron can be generated. What are they? Temperature. Other one is voltage, field. So one is a thermoionic emission, the other one is a field emission. So you can have a thermoionic emission gun or a field emission gun. Both of them will give up electron. Process is different. One gets energy in terms of thermal, another gets energy in terms of an electric field. Right? Now, how about the energies of these electrons? SEM versus TEM? Energies of the electrons? Anyone? So the SEM uses energy in the electron of 20 to 50 kilo electron volt keV. Okay. However, a TEM will use energy in the range of 200 or 300 kilo electron volt. Okay. Now, why do we need more energy in case of a TEM? Because the electron has to penetrate, right? One more thing. Sometimes we think that if it has more energy, it is like a like a force that it will just penetrate through because it has more energy. Actually, it is not like that. It also has to do with the wavelength of the electron. Okay. So higher the energy, what happens to the wavelength? Lower the wavelength, right? So it has to do with the wavelength of the electron as well. So it is not like, oh, we have higher energy, so I will go through. Okay, it has to do with the wavelength of the electron as well, because the wavelength of the electron or wavelength of electromagnetic radiation determines how the radiation interacts with any material. So that is why a microwave can heat up your insulating or ceramic boards, for example. But in case of a metal, what does happen? It catches fire. It heats up. I mean, there is some kind of arcing and all those things. Right? So the same microwave is reacting or responding to different materials in different ways, right? So material property corresponds to matching with electromagnetic property determines how it interacts. Anyway, deviating from the discussion. So now again ACM versus TEM. Sorry, why would I use ACM? To study what? Surface morphology is the most common use of ACM. That, for example, if I have a very thin film, a plain surface, I can see how it looks. If I have some particles, for example, some of you may work with nanoparticles, I don't know. Then how does the particles look? Does it have tentacles? You know, this is not only limited to material or electronics. It also finds a lot of application in terms of biology, right? So, for example, when viruses are scanned, we use ACMs, right? So we'll have some images after this where you can see how ACM, what ACM can do. Why would I use a TEM? Grain level, yes. Atomic level, not. Grain level, yes. So even when you want to see even smaller structure, right? Smaller morphology, smaller structures, we go for TEM. Okay. Second thing is SEM can also give us information about device structures. So, for example, if I have a transistor, three-dimensional structure, I put an electron beam on an SEM electron beam. The way these electrons are getting scattered and the entire, there's like a cylindrical, hemispherical collector that collects this scattered electrons, and then I can map in 3D how that device looks like. Right? It is the same thing like you can do with light, but at a much smaller scale. Right? So I can also make 3D, device dimensions can be found out using ACM. But TEM is generally not used for that kind of application. Okay? Now, ACM can have another added feature. Do you know the name? Yes. That's an additional feature, yes. But ACM can have, so I think the next slide we have that. So ACM stands for what? Secondary electron. Correct? There is another process which is similar and is used in conjunction with ACM. It's something called backscattered electron. Okay? Next slide you can see. So that backscattered electron microscopy, right? If I have a backscattered electron probe along with the secondary electron microscope, what I can do is not only I can measure the different dimensions, I can also differentiate between very similar kinds of material. Okay, so it is like, for example, I have if I have silicon, some metal, and some oxide, let's say, this device, using a secondary electron microscope, I can get the structure, physically how it looks. But it can be sometimes very difficult to distinguish between two different materials. Okay? Difference between two different materials sometimes can be vague in a secondary electron microscope. But if I have the backscattered electron provision there, what I can also do is I can also see which one is silicon, which I will not really know it is silicon. What I know is that this material is different from this material. The energy of the electrons that are scattered from here will be a bit different from the energy that are scattered from here, backscattered. Okay. From there, I can say that this is a different material, this is a different material. I can represent them in different colors in a map, for example. But I will never know it is silicon or it is oxide or it is metal. That I will not know. That I will not know. But I can distinguish two different kinds of material. Okay, having the backscattered provision. So here are some images, for example. So here also I'm not showing a device here, but we will see some ACM images in the next few slides. So here, for example, is a TEM image, and I am looking at a cross section here. And this first layer, if you can see my pointer, this is just 2-3 nanometers. Okay. The second layer is the magnesium oxide. This is also 2-3 nanometers, and this is iron platinum. This is around 6-7 nanometers. So basically, with the TEM, you can see very thin films from the cross section, from the side. Okay. So on the substrate they are there. On the side, from the side I can see them. So I can accurately determine what are the thicknesses, for example, of these films. So that's one, and also one use of a TEM that I can do. So here I have pointed out what are the uses. So for example, using ACM I can find the shape, I can find the structure, I can find the morphology. With a TEM I can find the shape, structure, morphology in high resolution. What I am missing here is also I can find the thicknesses of very thin films. Okay, that is also something I can do using a TEM. There is something called AES. Have you heard of AES? Have you heard of AES? The full form is Auger electron spectroscopy. Heard about it? Heard? So Auger electron spectroscopy is another one that is used in the industry on a regular basis. The purpose is, do you know what is the purpose? The purpose is for composition and analysis. So here using AES, you can actually determine what is silicon and what is silicon oxide. Right? That ability is not there from a ACM or a backscatter scheme. But your Auger electron microscopy can say. Now someone said that we can use EDX with the ACM, that is true. And that also gives us the composition. Okay? I will come to the difference there also. Now that gives us the composition, yes. Along with, and then this EDX can also be used in TEM also. Okay, so you can train, you can fix your field of vision in the TEM also to a very small region, few nanometers to tens of nanometers, and then you can also perform EDX on that limited region, and again find out the color map of different materials. Okay, so that is also possible. EDX can be used with TEM and SEM both. Now, what is the difference between a TEM and EDX and AES? Both of them can be used for composition and analysis, that is true. But there is still a difference between EDX and AES. See, why I am discussing, I am trying to discuss not from a theory perspective, I am trying to discuss from a use perspective. Okay, because theory perspective is very easy. It is there. You just Google up these words, you will find all the details. But what you will not find is when to use what. That information I think is more necessary. Right? So that's why I am trying to go from that direction. So when would you use AES and when would you use EDX? See, I will give you the answer. AES can give you composition. At the same time, it can also give you stoichiometry and the bonding state. Right? So if I have silicon oxide, is it SiO2, is it Si2O3 or some other composition? Right? The stoichiometry. Right? That can also be found out using AES. In what bonding state silicon is? In what bonding state oxygen is? That can be found out. EDX on the other hand will only tell you this is silicon, this is oxygen. What state they are? EDX cannot tell you. Right? So there draws the distinction. So if you want to only find out which elements are present, go for EDX along with ACM or TM. If you want to find out in your film or some region in your device, what is the composition state, then you need to go for something like an AES or an XPS. We'll come to XPS after this. Now, one more difference. AES is a surface sensitive technique. It can only measure the surface of anything. Anything below few nanometers, it cannot sense. Okay, that also we need to remember. If there is some kind of a capping, some kind of, because many times our films are, our devices are protected by some kind of an oxide, some kind of a sacrificial layer is there, which is dispensable. We don't have any functional use of that layer, but it is there to protect the layers. Okay, but that can limit your probing technique, because there are some techniques which are only surface sensitive. Okay, so that also we need to remember. Okay, other than that, the entire electromagnetic spectrum has different different uses. So there is sorry, there is photoluminescence, okay, which uses the visible one. Then you have XPS using the X-ray one. You have you have XRD, which again uses the X-ray one. Okay, fine. Now this is an image taken by using a SEM, and you can already understand what this is, right? Huh.
So what is the difference between the ACM, TM and STM? There is scanning tunneling microscopy.
So scanning tunneling microscopy is more, so someone say atomic imaging. Now if you really want to find how your atoms are stacked one with the other, that's when your STM can come handy. So STM is a very powerful technique. Again, it uses tunneling electrons, but at the same time, it has some. It combines the properties of both scattered electrons, tunneling electrons, and it uses some kind of reconstruction, some modeling. So with those powerful techniques combined, what we can actually do is we can image atom by atom, how they are stacked. You know, so that STM is very powerful and very rarely available. I mean, very specialized technique. But yes, if you really want to see how your atoms are stacked one above the other, or how they are really, like the biggest zoom possible, then you have to opt for STM. Okay. So you can already now read what this is. What is this? Eyes of a fly. So I don't know if you can appreciate. Can you see like these minute details in its eye, right? And also this very tiny hair it has there, right? All of this actually helps the fly for vision. So these are its receptor cells, but at the same time these hairs also play a part how to see. So these kind of things are possible to do with a SEM. Optically, you will not be able to do this. Why? Why cannot I do this with the optical microscope? Yes? Wavelength, yes. So it comes, the resolution in any of this probing technique will come from the wavelength, the lambda. Okay. So the smaller the lambda, the smaller feature I can measure. Right? Now the wavelength divided by 2 is kind of called the resolution limit or the diffraction limit, beyond which we cannot image. So if my wavelength is 400 nanometer, then I can only image to a resolution of minimum 200 nanometer. Lower than that, I cannot resolve. Okay, if something is 50 nanometer, 100 nanometer, I cannot resolve that or I cannot image that using something using a source which is 400 nanometer in wavelength. Okay, so lambda by 2 is that limit. And I have also just mentioned to you that the energy plays a role in determining the lambda, right? The wavelength. Okay, so lambda is given by this relation where lambda is equal to h over root over 2 m naught E. E is the charge and the capital E, which is the energy. So more the energy, smaller is the wavelength. So therefore, the optical wavelength is not enough to measure this. Okay, so we go for electrons, and by increasing the energy of the electron, we can make the lambda to be smaller. Okay, so therefore ACM and then therefore TEM can have even smaller resolutions or higher resolution but smaller lambda by 2. Okay, now yeah. So see, this is what I mean. This is the zoomed in image of this one. So this is at a higher scale, and then when I go further, I can see in more detail on the head of this fly. Okay. Okay. So then I just mentioned to you that SEM can detect secondary electrons as well as backscattered electrons. No. So see, this is sorry, this image is not very clear here, but let me try to still try to say what I'm trying to say. So this is something called the interaction depth, okay, or interaction volume. So depending on the source, it will have different kinds of interaction. So see, this is the electron beam, okay? The electron beam is coming here, and when the electron beam falls here, most of the interaction takes place here, okay, on the top surface, and the result is that secondary electrons, this red thing, okay, this red thing is the secondary electrons. This is coming out from here. Then there are these Auger electrons which are coming out from even top of that. Like the first thing that is coming out is the Auger electron here. Then is the secondary electron, this part. Okay. And then from this part there are backscattered electrons. Then there are other kind of X-ray based energies, photons that are coming out, so and so on. So what you see basically is that the Auger electron is coming right from the top. Then is coming the secondary electron, and then coming the backscattered electron. And from the very depth of it, sometimes X-rays can come out. Okay. So now my choice is which one of them I take. Each of them will give me a different information. Each of them will give me different information, right? So the probe here is the electron. In some other case, the probe can be light. Okay, the probe can be X-ray, and similarly, there at different volumes, different energies or electrons will come out. My choice is to take which one and understand what. Okay, so the secondary electron, as I told you, gives you more about the morphology, the structure, this kind of things will come from the secondary electron. The Auger electron, which is coming from very at the top of the surface, that is measuring more the composition and all those things. Okay? And then if you have the backscattered electrons, it can also give you some information about difference between two different materials. Okay. Now some of the electron SEMs, they are based only on secondary electrons. Okay. So they are based on the inelastic interactions of the of this incoming electron beam with the material. But some of the SEMs can also use backscattered electrons, which are basically originating from elastic interactions. Okay, and the second thing is that they have high sensitivity to difference in atomic number. So that's why I said you can differentiate between two different atomic number materials because of the backscattered electron. Okay, from the same probing actually I am getting. So if you have a SEM, if you have ever seen a SEM, or if you have used a SEM, the same SEM is generating the backscattered electron. If you do not have the backscattered provision, it only means that you are wasting the backscattered electrons. You don't have a collector to collect that backscattered electron. If you are able to collect that electron, you will also get the information about the difference in the atomic number. Okay, but this is not quantitative, so you will not know what is silicon, what is gold, what is platinum, what is oxygen, and so on. What you will only know is that they are different atomic numbers. So you can use you have color map showing that these are different materials if you use a backscattered electron in addition. Is it clear? This one? Okay. Next is that SEM examples. Okay. Now why do we use SEM? So I told you that when the wafer comes, I also need to find out defects. So if you see there are some patterned structures here. So you see these places, right? These definitely are defects, right? We don't want them to be connected, but they are connected, and this connection can mean so many things. But in essence, what it will do is the device properties will be undesirable, anomalous. Whatever I want will not be true. Correct. So that's what these kind of defects will create. Similarly, there are many other defects that are shown here. These are all taken by SEM images, and this is what the industry does on a regular basis. It takes out their silicon wafers, does SEM images. After many different layers, okay, different layers are made, and and different devices are made. Maybe 50 different steps are involved. But at each step, they are trying to take out one or two wafer from that batch on a regular interval, and then they are using this kind of SEM imaging technique. And this is done manually. This is not done so far in an automated manner. There is a batch of R&D engineers, for example, who will be given this. Every day they will give them samples from batches, and they will scan it, and then they'll give the report. Okay, based on that report, that batch, it will be known that that batch has this, may have this defect or may not have this defect, and so on, and accordingly they will be sent to the market. Okay, so therefore this kind of SVM images are very necessary to really see, if our products are having any anomalies, abnormalities or not. Okay, so material structural imaging therefore is carried out by SEM on a regular basis. Okay, yeah, so here I still have it in a better manner, this image. So you see here again the same things. So electron beam, OJ is going here, the secondary electron, backscattered electron, even from deeper there are characteristic X-rays and so on. Okay. Now let's see, here I am talking about only an electron beam. Now there are different kinds of probe beams we already discussed. One is the electron beam, one is a photon beam. Here I am saying X-ray, but it's a photon beam. So photon can be light, photon can be X-ray, right? Photon can be in any other wavelength region, right? So that's why in general I call it a photon. And then we also have what we did not mention, I also forgot to mention that, is ion. Ions can be also used to probe properties, okay? One example of that, can you give me an example where ion is used? I think I mentioned this one in the last class here. Last week somewhere I mentioned this. Anyway, can you mention one technique where ions are used for probing? Okay, is it Morse-Bohr? Morse-Bohr, no, I don't remember at this point Morse-Bohr actually. I don't know. I have to check, I'm not sure. I will not comment on that at this point. The one at least I can cite at this point is called secondary ion mass spectroscopy. Okay, some people may also call it as SIMS, SIMS. So that again is a very commonly used tool in the semiconductor industry. Okay, and the use of SIMS is again elemental composition. So elemental composition can be found out using SIMS, secondary ion mass spectroscopy. Okay, so there the source is an ion, right? So three different sources I am mentioning: photon, electron, and ion, which are the probe beams. And the analyzer therefore can take everything. The analyzer can take the electrons. The analyzer can take different energies of photons. It can be X-ray, it can be optical, whatever is coming out, right? And it can also take some ions, if some ions are coming out, right? So the probe can be of multiple types. The analyzer can also be of multiple types. There are multiple permutation combinations, not combination. This will be only permutation. Actually, combination also, because the order matters here, right? So there will be multiple combinations or permutation combinations of this one that will work. And what also comes in difference is that the interaction depth. So see, if I am using an X-ray, if I am using an X-ray as the analyzed response, then it is coming from a very deep volume. Okay. Whereas if I am using the OJ, it is only coming from the surface. Okay. So the depth that an OJ can, let's say, analyze is only 4 to 50 angstrom, which means in nanometer. In nanometer, how much would that mean? 4 to 50 angstrom. How much? 0.4 to 5 nanometer. Correct? And how many atomic layers do you think that will mean? Approximately one atomic layer is no smaller, because atomic radii goes up to let's say 0.3, 0.4 angstrom. So if I assume that all of them are uniform, then it is let's say 0.4, 0.5. But if they are not uniform, then maybe you are right 10 angstrom. Okay, so let's say 0.5 angstrom. So then I can image up to maybe 10 atomic layers by using an Auger electron spectroscopy. Okay, but if I want to probe deeper, then something like the X-ray, that is EDX for example. EDX is basically what? It is using the electron beam as the source, but the X-ray that is coming from very deep is being used as the analyzed response, let's say, right? So EDX therefore can measure up to a depth of around 5 micrometers, right? Now 5 micrometer is 100 times of 50. No, how much did I have here? 1000 times of 5 nanometer, correct? So your EDX, that means when you are using the same electron beam, but you are measuring the X-ray response, you can measure to a depth of 1000 times that you can measure with a AES. That is what I told you, the difference between using AES and EDX. Remember that, right? That is the difference. AES is surface sensitive, EDX is depth or volume sensitive. Okay. Okay, fine. I will skip this one because this will take time. I will also not go into the detail of. So, if you are interested, you can find out how the Auger process takes place. It is an indirect process. Okay. I will not go into the detail of this one now. I am just focusing on what they can do. Okay. So yeah. So this is how like if you measure AES, then this is how it will show. It will show you different peaks. And from there you can say, for example, sulfur, nitrogen, oxygen, silicon and oxygen and so on. You can identify. Okay. And if you do more detailed analysis, you will be able to find out what are the states in which they exist. This is of cross section. So let me see. Yeah. So sometimes you can have. So sometimes I can cut like a cross section of a device, and I can. So let's say this is my device, right? Okay, this is the chip, and this is the device. And if I cut a section of it like this, and then I take a Auger measurement of this one like this, I can see also the different layers from the side view. Okay, so this is what it is showing. So okay, now let me ask this. Just now I mentioned that if this is the device, I take a cross section of this, I can now put the beam on this and I can measure the Auger spectroscopy. Why do you think I would like to do this? Use. Because I am focusing only on the use. Why would I do something like this? Right, something like this, right? I am measuring across the cross section of the device. Why? What does AES give? Sorry, what does AES give me?
Composition surface.
Composition
to surface.
Composition at the surface, yes. So that is, I've cut this cross section. Now if I probe here and they just take the Auger electron, I will see what is the composition here on the top. That means this top is basically this edge, right? What information will I get from there? Why will I do that? See, our devices can have up to 10 to 50 different layers. Very thin layers stacked above each other. Okay? 3 nanometer, 2 nanometer, 5, 10, 15 nanometer, maybe I don't know, not okay. But different layers can be there. Right? And then there are different vias and channels. Right? Because this is 3D. Okay, one channel might go like this, the other channel might go like this, right? So it's a three-dimensional world there. So now when this is there are multiple layers, multiple films on top of each other. What happens very often is these devices, they are while processing, there are sometimes you subject them to some kind of temperature, some maybe sometimes 200, 300 degree temperature also they are subjected to. So what does temperature cause? Vibration, yes. But at the atomic scale, what would vibration mean?
Crack.
Defects is too much high, yes. But I'm not talking about so much high energy. Let's come down, let's tone down the energy a bit. So atoms are getting more energy, right? Each atom is getting more energy, the thermal energy is more. What would it do? It would expand. Expand. See, atoms don't expand. Atoms don't expand, right? What it would do? Materials expand. So what does that mean? What is the atom doing? Correct. So the atom is spreading. Atoms are going away from each other. So in a thin film, that would cause something called diffusion. That means some of the materials will try to move from one to the other. Spreading, So spreading, right? Diffusing. So now what would happen if your material diffuses from one to the other? What will happen? Your material properties are getting changed. Your conductivity, for example, you build a capacitor. Somewhere it was supposed to be a capacitor just below the gate. Now that dielectric constant has changed. So your device is defective. Right? So how do you know? Sometimes you have to check. No? Is my process causing diffusion? How do you know? Like this. You cut a cross section. You get a map like this, right? Something like this. You know if your lines are like this or they're spreading. So, for example, if they would have spread, then you would have more mixing, isn't it? Or else you would have these discrete colors. Correct? Because different materials are shown in different colors here. So these colors will be distinct. Otherwise, they would be matched. Or maybe at some places you will see that the colors are protruding into each other, right? So that way you are able to determine if your layers are actually diffusing into each other. So that's why we will do a characterization like this. Okay. Are you able to understand why I am trying to do this? Right? So that's why this kind of cross-sectional AES is also done. Okay. I will not go into what kind of analyzers we have. This is making on share. Let's forget about this. Okay, so then the other one I talked about is XPS, right? So you see here, in this case, now the beam, what is the probe beam? X-ray. Okay, photon rays, X-ray. And what is the interaction depth? What is the interaction depth? Ten micrometer. I don't know if people from behind are able to see it. So it's written here, it's 10 micrometer. So the interaction depth here is 10 micrometer. So because X-ray is the probe, so the interaction depth has become even bigger. Okay. So here the X-ray is the source and photoelectrons are the what? Output measured response, right? Yes. And if I ask you what kind of effect do you think it is similar to? So, okay, let's see this. I don't know if again you see this equation or not. Are you able to see this equation here? From the back, can you see this? Yes or no? No. Okay. So I will read it out for you. It says KE. Okay. KE, and it says KE is measured. Okay. KE measured is equal to H nu known in bracket. Okay. Minus BE, which is the binding energy, and there is some kind of a constant which is calibrated. So let's forget about the constant. So what we know is that the kinetic energy is equal to h nu, that means some kind of energy, right? Minus the binding energy. Okay. So what does the h nu represent here? The incoming beam. And since it is the X-ray that you are providing, you know what is h nu. Nu basically corresponds to the frequency, right? So you know what is the frequency, and you are measuring some kind of kinetic energy of the electron that is coming out. Okay. So if you subtract the two, there is some constant there. But forget about the constant. If you subtract the two, what you get, the difference that you get is basically the binding energy, and the binding energy will give you what? The binding energy will give you what is binding energy? The energy needed to from the surface. Right, so the energy that is needed, let's say, to strip that electron from the influence of that nucleus, right? That is specific to every element, isn't it? Correct? So therefore, from there again we can get the elemental composition of that material. Now, if it is in a binding state, this binding energy will not. If it is in a bonded state, will the binding energy be different or not? Different, right? Definitely different. So therefore, XPS can also give you the state of that element, right? 2 plus, 3 plus, whatever it is, right? So you will also get that information from this measurement. Okay. Now, this and AES, what is the difference? AES also can give you the same information. No, let's say I'm holding an examination. The examination is already over. But let's say I'm holding an examination mock, and I ask you a question that what is the difference between AES and XPS? You give me 3 points. What would be your first point? Let's say. Just louder, no? 1 point. So the first thing is you're distinguishing what is the source. The probe source in AES is electron or electrons. The probe source in a XPS is photons or X-ray, right? Second point. Let's simply go by the analyzer. What do we analyze? In AES
Composition.
no, but that is the what you are measuring. What I'm saying is that the analyzer, no, analyzer is the response. The analyzer is getting some electrons. So in both cases it is electron, but in AES it is a special kind of electron. It is called Auger electron. The emission is Auger emission. Okay, and I did not go into the details of the process how it happened. But if you see there, it will see, it's actually shown here. See, the photoelectron is directly removed, correct? Directly removed, photoelectron. In an Auger case, it's here, Auger case. What is happening? The electron is not directly removed. What is happening? This electron goes here, and this electron goes out. Right? Yes or no? So first thing is, this is a direct emission, this is an indirect emission. The electron energy is higher in which case? This or that? The emitted electron will have higher energy in this case or that case? XPS will be right. In the first case, in the XPS case, the electron which is nearest has gone out. Right? So the highest energy difference comes here. Here the net difference is subtracted between the two. Right? So the energy band in which these electrons are collected is also different in Auger versus XPS. So one is the Auger electron, the energy is generally lower, some few EVs, let's say, I don't remember the range at this point. But in XPS, Also, it is in few EVs, but the range is a bit on the higher side. Okay, and those are photoelectric. Okay, so that's the analyzed part. So these two differences. Third difference is
XPS can probe deeper.
correct. XPS can probe deeper. The interaction volume there is 10 micron. Okay, if not 10, at least 2 microns. AES is only surfaces. Okay, so again depends on application. Where now I don't know. Do you have this question? Any questions here? I know it's already overload on Bihu Eve. I understand Jalukbari rather, but I understand that part. But just 15 more minutes for me. No, 10 more, 10, 15 more minutes. Okay. Any question?
Go beyond the protective layer that you were speaking.
XPS can go yes, but AES cannot. Because AES will be limited to the 5 nanometer. See, one question that sometimes I get is that why would I use XPS? Because why would I use AES? Because my XPS can go deeper and measure everything. Why would I use AES? What would you answer? Why would you?
Topology of the surface, where yes.
See, AES is also not giving me topology because for topology of the surface I use ACM. Right? AES and XPS are both giving me elemental composition as well as documented, the one is. The interaction volume of one is higher, XPS can go deeper, AES is on the surface. Now my question is, why would not I use only XPS? Because XPS is measuring the surface as well as the depth. Huh?
What is 2D materials?
2D materials, yes, good, but can you elaborate why?
If it is two-dimensional, you can use one type, but if it is volume, you can choose another type.
So probably what you're trying to say is because 2D materials are let's say one dimension very small, that if I am trying to probe it and below that it will be from a substrate.
Yes.
So my XPS will give me more information from the substrate rather than the film itself. So that's one reason. The other reason you think similar lines only. I told you that devices have multiple layers. Right? Now if I am probing from the top, for example, and I want to look at the top surface only, I just want to understand what the top surface composition is. If I use the XPS, the information will come from the entire one. All the layers are sending. So it is hotspot. It's like too much noise. Okay, maybe the top one will give me more information, the bottom one will give me less information, but there is still a hotspot. There is so much unwanted information there, right? But if I use only AES, I will only get the information from the top layer. Right? So it's basic. Wherever I use, whatever I use, I will use accordingly. Right? Okay, I'll not go into the physical case. Let's forget. Depth profiling. Okay, so I will also skip this, but I will simply say that sometimes you can, sometimes you have to, you have a device and, okay, I'll just elaborate this example only, the one I just told you. Multiple layers, I probe with an AES from the top, okay, I will know the top surface. Yes? Or no? Yes. I want to know the third surface. How will I do that? Third layer. And let's say each layer is 5 nanometer thick. Third layer, that means between the third layer and the surface there is 10 nanometer, isn't it? How will I probe the third layer? Option I use AES, it will not go inside. If I use XPS, it will measure everything below this also. How do I measure the third layer? I'm interested in the third layer. Huh? TM will give me the, how does it look and everything. Elemental. Maybe then you will tell me, okay, I will do a TM VDX. Sure. But very difficult. That is not something that I will generally use. Yes, that can be done. If I do a TM, but making a TM sample and then looking at the thin layer, very critical. That's why I cannot make a VDX.
With closer synthesis very carefully. So this
yeah, but here this is solid state devices, okay? These are multiple layers. So in that case, we do something called depth profiling. Okay, and in depth profiling, there can be two ways of doing this. One can be destructive, one can be non-destructive. In a destructive method, as the name suggests, I will remove the first two layers. And the way to remove this is something called etching. You may have been taught something about fabrication and all those things, isn't it? So they may have taught about physical etching, chemical etching, reactive ion etching, right? So that kind of etching I can do. I can use some argon ions with some energy and scrape it out. Okay. So the top two layers can move. Huh? And once the top two layers are gone, I can remove the third layer with the AEC. Yes? Any challenges you see with that one?
You can damage the third layer also.
It can damage the third layer, first thing. Second is that when the argon ions are coming, breaking of the first two layers, it can also embed some of the first two layers in the third layer. That is also possible. That happens. Okay. But that is a technique it is used. Okay. The second way is a non-destructive way. Okay. And here what we do is a angle resolve measurement. Angle resolve measurement. So if you are using angle resolve, see same XPS, you are using angle resolve. So every time you are, so this is your sample. Here you are measuring like then you tilt it. Again you measure like this. You tilt it another angle, you measure like this. Every time the distance of the surface to that layer is increasing. So that distance is then used because there are two different intensities, and we have equations which can correlate that distance with the intensities. Okay, from there, from that two differences, we can also estimate the composition of that particular intensity, particular that graph, because there are multiple peaks, and the intensity of the peak will keep changing depending on how deep it is from the surface, and by changing the angle, I can do it. So that is a non-destructive method. Okay, so these are two different methods that are used. Okay, I explain this in briefly, but I will share the slides. You can go through them in detail if you want. And just now you talked about damages. Yeah, this kind of damages can happen. You see, this is a crater created by the argon ions. So you see how badly damaged it is. Okay, this is the ACM image. Okay, TM I will not go into, but I just briefly discuss what TM is. There are two kinds of TM that is done, bright field and dark field imaging is done. Okay, dark field imaging gives us more structure based information. It can sometimes complement XRD as well. Okay, and bright field, here you see bright field and dark field imaging. Okay, these are examples. I will just skip this one, photoluminescence. Okay, sorry, I'm skipping all this because we just don't have enough time. These are some magnetic one. I already mentioned that day how a Faraday's coil can be used. When a magnetic material is there, and in vicinity of that, you take a current carrying coil, pass current I through it, and you make it vibrate near the magnetic material. Okay. So what will happen is that the magnetic field from this material will change the flux in the vicinity of this current carrying coil. And that current will therefore change according to Faraday's induction law. Okay, so that current can therefore be that will induce the voltage, and therefore that can be measured as a in terms of how much that magnetic field is or the strength of the magnetic material is. Okay, so that is called vibration sample magnetometry or VSM. So this is the structure you see. Okay. I will skip this one as well. Yeah, so Hall effect someone mentioned. So Hall effect is also another measurement which is used to measure, let's say, the mobility and all those things. Again, unfortunately, I cannot cover today. One more thing I would like to mention briefly here is that, see, I don't know, maybe you are aware. So electrical measurements are resistivity. Okay. So how many of you have done resistivity measurements? Anyone? Resistivity? No? Conductivity, resistivity, nothing, no? Okay. So I just ask you. So let's say I have a semiconducting material. Okay. And I have two probe tips, like a multimeter tip. Okay. But think of it as a very miniaturized multimeter tip. Very thin. That, and I have to see it under a microscope. I put it on the substrate of the silicon or any semiconducting surface. can I directly measure the resistance of this semiconducting material? Yes or no? Yes? Yes? Any yes, any no? Everyone else is nota here? I have a feeling that you do have election duties? Yes. So then on the election duties you are on the other side only, you are not on this side. You are not voting. I can see that. Only taking the votes. Okay. So any yes, any no? I have only one yes here. See, the answer is no. You cannot do it. The reason is that the moment you connect these two, you are creating a junction there, and that is not a metal-metal junction. See, when the metal-metal junction they come into contact with each other, the work functions are different. Some electrons can flow, and it's a free flow of electrons. In the case of a semiconductor and a metal, what do you form? You form a metal semiconductor junction. Correct? So you already know that metal semiconductor junctions are not so easy. There can be barriers. Right? Second is that the contact resistance will have a barrier which will present itself as a resistance. Okay? Then the probe itself have another resistance. Third thing is the moment you put that if there are some electrons are flowing, they don't have a formed channel. They don't have a single path through which they will flow the electrons. They will spread everywhere. And obviously because it is not a metal, they are not neutralized. Right? They are spreading unevenly. So what happens therefore is that the resistivity or the resistance measurement carried out by two probe is never enough. What we need to do is the solution is have multiple probes. We have 4 probe measurements, 6 probe measurements, and so on. So that's why this kind of bar will have multiple like outlets or kind of hands like this. Okay, and these geometries are very important. I cannot cover it in this class or this lecture. But these geometries are also important. These dimensions all have some proportions. There is a minimum and maximum limit beyond which or less than which or more than which you cannot go in terms of the ratio of the length by the breadth or by the arm length by the arm width and so on. Okay. So these things, I am not discussing the details here, but just keep in mind these are also critical in terms of this kind of measurements. Okay. Quickly the challenges. So the topic is environmental factors of that can affect the device characterization. What can affect? Temperature, humidity, Northeast, Assam, both are very difficult, especially in summers, right? Then chemical exposures. Okay, chemical exposures as in like in the environment, if there are some, I don't know, like some people say construction is going on. There are so many things that are floating in the air, right? Then there are hydrocarbons that can float in the air. Some places it is more, some places it is less. Some sulfur compounds, right? Some carbon organic compounds. So all of this can have some kind of effects on your device performance, right? Then the electromagnetic interference, electromagnetic radiations. So these are all different kinds of factors that can affect your devices, and there are so many other methods that we use to deal with them. Okay. I will share the slides, so please go through them in your own time. And what I will simply now go through is maybe this one, future one. So in the future, what we are now trying to look at, how the future of characterization looks like. The basic characterization techniques are more or less established. Okay, but what is coming in now handy is imaging of 3D structures. Because today we have heterogeneous integration, something called heterogeneous integration. So there 3D imaging is very important. So that is one work where many kind of techniques are coming, like tomography, X-ray tomography techniques are coming. Okay. Then we are also using machine learning and AI in characterization techniques today. So sometimes, for example, there are some places, say I took an image and the image is not so clear. Okay. AI and ML can come in and help me in clarifying that image. Because AI and ML has learned from different other sample sets before, and now it knows how to reconstruct that image. Okay, so that kind of techniques are also now being, or additions are now being made. Another is in situ characterization. So sometimes during the making of the device itself, we might have the probing techniques inside, so that when we are making it, we are probing it at the same time. Okay, so in-situ characterization is also another thing that is being done. And yeah, so then there is another place where the quantum and nanoscale characterization is something that is being hugely discussed, because in the quantum world our normal characterization techniques are not working. We are finding new characterization techniques that can be used there. Okay, so for example, your mobility equation doesn't hold in terms of quantum electronics, right? When you're talking about, say, the mobility of an electron in a two-dimension, in a three-dimension, let's say, that equation is very different when you talk about a nanoscale transport in a quantum material and 2D material, right? So then proving that it becomes very difficult, because your normal equations or normal classical approaches are not working. So those sensing techniques or those characterization techniques have been developed. Plus, there is also a collaborative approach across the research communities and governments around the world to standardize the different kinds of techniques and also metrology standards. Okay, so these are the things that we look forward to in the future. And I think I will end it here. If you have any questions, please shoot them. And if you think that if you shoot questions, your colleagues are going to pursue for that because they extend the session, then please feel free to drop a message or an email. I will be happy to answer them. Okay. So thank you. I will end the session here. If there are any no questions, otherwise we can take a question, or else we can stop it here. Okay. Thank you.
Thank you very much, sir. And special thank you to you because you have adjusted your time.
Thank you so much. You have thought that I can be someone who can help with this.
Thank you, sir. Thank you once again. So, ma'am,
Sir, only one question, sir. Why it is so costly when we go for sample?
Because the equipments are very costly.
One for outsiders.
We try to have different kinds of. I don't know if we're talking about IIT as such. Most of the places, these are very expensive equipment. Even it's like having a white elephant. Really, government will give you the initial money. Every year, it needs lakhs of rupees to just maintain it.